Um, Welcome everyone to our first in this series of public lectures that's being organized in association with the National Space Science Exhibition. We are just going to start in time because we have a tight program today, and this is also being streamed online in YouTube. So let me briefly talk about the National Space Science Exhibition, which is an unprecedented collaboration between ISRO Kolkata, ISRO, Asian Bose Center for Asian Bose National Center for Basic Sciences, Presidency University, St. Xavier's College, Calcutta University, in association with the National Council of Science Museums, Ministry of Culture. We have events going on throughout the week at Science City, at the Bhalerao Industrial and Technological Museum, as well as various partner organizations where we're hosting public talks. The main science exhibition is happening in Science City, which started off today, and is going to continue until Sunday, which is the 11th of December. We have organized for passes for students and faculty and staff from the partner organizations. So if any of you are interested in coming to the exhibition, all you need to do is just turn up at Science City and contact our help desk in front of the ticketed entry gate, and we will be ready with passes which you can give to you to come and enjoy the space science exhibition as well as participate in the public talks that's ongoing. Some of the important events are Women in Space Sciences panel that is happening on 9th December morning at the Bhalerao Industrial and Technological Museum. We have a Science Adda in Bengali at the fountain area of Science City in the Saturday afternoon, that's 10th December. We have an Industry Academia Relations panel on Sunday at the mini auditorium in Science City. And beyond that, we have multiple different events that's happening throughout the city. I would encourage you to just go ahead and look at the schedule of the exhibition. Don't miss any classes for doing this. But beyond that, you're welcome to come and visit Kolkata and enjoy the exhibition. With that, I'll invite Rajesh to come on stage and introduce our speaker for today, Varun Bhalerao from IIT Bombay. Rajesh.
Welcome you all. So it gives me great pleasure to introduce Varun. I've known him for some time. So currently he is a faculty at IIT Bombay. So he is involved with the very ambitious Daksha mission, and they are developing one of the most sensitive high energy transient telescope to keep track of high energy observation in the universe. So he is an alumni from IIT Bombay. He did electrical engineer, and then he did his PhD at Caltech. There he contributed to some of the space missions. One of them is NASA's New Star. He developed this is complicated for me, some cadmium zinc telluride imager for AstroSat, that is an Indian multi-wave space telescope, which is a very successful mission. So Varun is a very actively involved in the astro instrumentation and also well recognized all around. He has received several honors, and Venu Bappu medal given by Indian Astronomical Society is one of them, which is the highest honor given by that society. He has also obtained several recognition, is a part of Academies of Science, Indian Academy of Science. He has achieved a DST Inspire faculty position, and he was awarded by IIT Bombay also Young Researcher or Early Researcher Achievement Award, and Kirti Ramatirtham Award for Creative Engineering. I have always enjoyed Varun's talk. I believe you will also enjoy. Varun.
Thank you. Hi everyone. Good evening. First is thank you for staying back. A lot of you have been giving exams, I hear, and usually after an exam I would not have wanted to walk into yet another talk, but yet here you are. So let me start with showing you just a nice video, right? If you are doing an astronomy lecture, you better have good pictures and videos to show. So what you are seeing is a time-lapse video from the Indian Astronomical Observatory at Ladakh, and this little telescope here which you are seeing in the foreground is something we will talk about later today, and you can see the beautiful Milky Way actually rising behind this. Okay, what I am going to talk about is, of course, how does the universe make gold from dead stars. Okay, and it's a very weird and a very fascinating story, because the universe always turns out to be far more imaginative and far more wild than we can actually speculate. So let's start with a pop quiz. Since you are coming from exams, clearly you would want more. What's your favorite element? Anyone? Oxygen. Somebody actually is awake. Awesome. Right? I was waiting for people to jump onto gold. I had like placed it there. But yes, oxygen, hopefully with some carbon, nitrogen as well, allows us to exist. But then if you take those basic things for granted, of course hydrogen, I was just drinking water before I came up. If you take all of those things which you take for granted, then beyond that we end up being quite a bit obsessed about gold, right? So where does all of this come from? Okay, and that's something that I am going to try to address over the coming hour or so. If you actually want to sleep off, then I will give you a quick answer. It comes from dead stars. How do you know? The poster already said that, right? All right. So to create gold, we have to take things back a bit, and to take things back, of course, we have to start with the Big Bang theory. How many of you have heard of the Big Bang theory? This one or the other one? Both of them. Awesome. Okay. So if we go to the Big Bang, of course, everything started from this one point. There was a Big Bang, and it created eventually the universe as we know it. Here is what the universe started off as with the Big Bang. Okay. So it created a lot of hydrogen. It created most of the helium that is presently there in the universe, and a little bit of lithium, and that's it. So for those of you who actually don't enjoy chemistry as much, if you were born 13 billion years ago, the periodic table was much, much simpler. Of course, you couldn't have been born, no carbon, no oxygen, nothing else. So we actually need to do something to make this picture a bit more interesting. So we need to start forging elements. Okay? How do you create elements? Any idea how elements beyond hydrogen came into existence? Fusion. Perfect. So here's the short version again. Hydrogen is a colorless and odorless gas, which I don't think you can read this, so I'll read it out. Hydrogen is a colorless, odorless gas which given enough time turns into people. Because that's what the universe started off with, just pure hydrogen, and here we are today. So what we then do is we take these giant clouds of hydrogen and any other gases that are out there, and just if you let them evolve under gravity, what you are seeing here is a cloud of gas and dust collapsing under gravity, and it formed these filamentary structures and sheets and so on. We have zoomed in on this animation a bit, and you can see there are blobs that are forming here. All of these blobs, and there will be hundreds of them formed as the animation continues, these are all young stars. Okay, these are stars which were born from the collapse of a single cloud. Whoops. And what happens is that as these stars then form, they are typically formed in groups, and you can see a bunch of them getting ejected because they are gravitationally interacting. This is one interesting thing. Most of the stars in the universe are actually born in clusters, and actually about half of the stars are present in binaries. So single stars are actually rare in the universe. So here's a huge cluster of stars that's forming. You can see that there are still things falling in, and a whole bunch of stars have been created here. Now inside this star is where all of this fusion takes place. We typically think of this as a simplistic picture. You start with 4 hydrogen and you get 1 helium. Turns out it will be a bit more complicated than that. So you start with 2 hydrogens, you make deuterium. From deuterium you would say, okay, let me go to tritium, but turns out you actually make helium-3. and then 2 of these helium-3s combine to give you 2 protons again and helium. Okay, so this is the main fusion cycle that happens, but gold चाहिए, hydrogen से helium तक पहुंच गए, we need to move on, right? So well, there is value in all of these elements. There is a lot of potential. We actually can make what we need from these. So the next cycle that goes on, which is, since oxygen came up here, that's great. So this is something called the CNO cycle. So what you do is you start with carbon, you keep bombarding it successively with hydrogen atoms. You go from carbon to nitrogen 13, then to nitrogen 14, then oxygen 15, and you come back to nitrogen 15, but then you lose helium atom here or an alpha particle, and you come back with carbon. So what's happened is that you got 1, 2, 3 and 4 protons, and you ejected 1 helium atom. Okay, this is one of the dominant cycles. This is present in the sun, in more massive stars and as well. So this is organic chemistry in a nutshell. Okay, everything else is just second order effects. Important ones because it creates us, but yeah. And then this keeps going on and on and on. Okay, so at the core of the sun, what's mainly happening is the first process we talked about, hydrogen fusing to give us helium. But then beyond that, the helium just sits there for a while, and then as the temperature of the sun increases, okay, there's no energy being produced, so pressure increases because the sun's outer layers are being held back because the center is very hot, so the pressure is high. If you are not producing energy, pressure increases a bit more as this outer layers start crushing the sun, so pressure and temperature rise enough to start fusing helium into carbon oxygen. From that, if pressure and temperature rises sufficiently, it will never happen for the sun, but if you had more massive stars, then you start creating neon, magnesium, and then beyond that you go to silicon and sulfur, and then you go all the way to iron. And you will have seen a variant of this plot at some point. This is the only technical plot that I will have in my slide. So don't worry, I am not making you secretly revise for your exams. But what you might have seen and you may remember from this is that if you actually do fusion, you release energy, and that is energetically favorable only all the way to iron. Beyond iron, if you want to create heavier nuclei, you actually need to provide energy, and that is a problem because you are trying, this is the fuel that is powering stars. So what you are trying to do is you are trying to convert hydrogen to helium, and that is making star shine, and helium to carbon, oxygen, and so on, the whole chain that we saw. So this is basically a star killer, because once you are reaching iron, you are stuck, you are not going to get fusion anymore beyond that. Okay? But then these stars can actually die, and in the death of a star, so you can have a massive star and it will refuse to play an animation, so we will leave it at that. But a massive star, when it has this inert iron core, okay, that iron is no longer going to produce energy. So the pressure, it's going to start cooling. When something cools, the pressure will decrease, which means the center is not high pressure enough. Outer layers start to crush it. Outer layers, on the other hand, have all of this material which we had here. All of this material can still burn. So when it enters that central region, it suddenly now ignites. By burn, I don't mean the kind of burning that you have when you light a match. By burn, I mean nuclear fusion, and that blows up the entire star. At this point, you have so much energy going around. You have so many high energy particles, photons and everything, that you really don't care about whether something is energetically favorable or not. So at this point, you do go ahead and make all of these heavier atoms as well. So now the periodic table starts becoming a bit more complete. So you have these massive exploding stars which marked in yellow. Now I'll explain this table a bit better. The color here shows what percent of that element was made by what process. So if you look at carbon, then you can see that somewhere around 25% of it was made in exploding massive stars, and about 75% was made in dying low mass stars. Okay, I am not going to go into how low mass stars die. They don't give us gold, so who cares? But if you have, by the way, I see a lot of you enthusiastically recording. That's awesome. It's all on YouTube anyway, so you might as well enjoy the live show. Okay, so you can have exploding massive stars here which would go as supernovae. These have to be 8 to 10 times heavier than the sun. Otherwise, sun-like stars, quite pithy on the scale of the universe, they die off in a very boring death as a nova maybe at best, as a planetary nova, sorry, not a nova. And that is what is going to give you some of these other elements. But we are still stuck going only up to here. We are getting very small amounts of elements up to here, and that's it. Technetium is weird, it doesn't exist in a natural stable form at all. Okay, very apt name, it was created by technology and it is a very, very unstable element. But we still are missing a big chunk of the periodic table here. Okay, so we need to do something more. Sona kahan hai? So we have made stars, we have killed stars, we still don't have that gold. So how do you make gold then? Okay, so let me write out a recipe for you now. Okay, and this is because I think I have stretched enough of your attention, you now probably want to sleep for the rest of the lecture. So first you start with a universe, and in that universe you make massive stars from hydrogen. Those stars synthesize metals. Now this is also where astronomers show their lack of vocabulary. The periodic table according to astronomers is hydrogen, helium, metals. Okay, so anything heavier than helium, anything that was not largely created in the Big Bang, according to us is metals. So you synthesize metals, then you blow up these stars, okay, and you spread these metals around. And this is important because any of the stars we see right now, they are not pure hydrogen helium stars. We have seen at least some traces of metals in every star that we have studied, which means that they are actually born from the ashes of first generation stars. Okay, so this material now spread out by the supernova explosion, again it will form a large cloud, that cloud will collapse under gravity, it will form more stars. So now you have the next generation of stars which have been created here. Now you kill those stars yet again. Okay, so again you blow them up and you create neutron stars. So now let's just keep track of things here, okay. This is sounding more and more like a Bollywood movie here. We formed stars, killed them, rebirth, killed them again, and we are still stuck with a periodic table that has no gold in it. No gold, no silver, no platinum, none of the things that you can actually make money for in the market. Oxygen, yes, awesome, but you know, if you try just selling like a gram of oxygen in the market, zyada kuch nahi milega, unfortunately. We live in a very weird world. So we are not yet done. So what do we do next? Well, how do you actually synthesize things like technetium on Earth? Any idea? Fission, okay. Fission ke liye you actually need already heavier elements, but you could do, basically you have to mess around with the nucleus, right? So you have to use particle accelerators essentially. So what you do is you collide particles together and you see what happens, and then ek particle karke karenge to bore ho jayega. So in stuff like say the Large Hadron Collider, you take thousands of particles, okay, millions of particles and collide them together. And come on, we are talking about universe, Big Bang, chote scales bahut boring hai. We need to ramp things up a bit. Okay, so how about we take something like 10 raised to 57 particles and then collide them together. Now we are talking. This, by the way, is more particles than are present on the Earth or in the entire solar system, about 3 times as much. Alright, so what you do is you take a couple of neutron stars. As the name suggests, these are stars made of neutrons. And you take these stars and you actually put them in orbit around each other, and eventually they lose energy to gravitational wave emission and they collide. So now you have the universe's greatest particle accelerator. You took 10 raised to 57 particles and smashed them together, and you can be very sure all sorts of weird things going to happen there. Okay, so that is where we are. So what you now do is you take those 2 neutron stars together, you make them collide with each other. The end product now is a black hole, and finally, as a side effect, you get gold. Okay, so how much gold, by the way, do you think is created here? So let's get some context. Okay, so but yeah, before that, you know, how do we know all of this? Right? This is now sounding more and more made up. कि ऐसे हाँ सुन रहे हैं तो चलो और बता देता हूँ. Let me take stars, kill them, reborn, kill, reborn. I mean, it's not exactly a prime time Hindi serial that you will keep watching no matter what happens. So we need to put some sense into this. Okay, so the way we know all of this is from gravitational waves and study of gravitational wave counterparts. Okay, that is my main area of research. So what are gravitational waves? How many of you have heard of a comic strip called PhD Comics? Oh, अच्छा comic रहता है, पढ़ो. So they had a very nice and simplistic explanation. So if you have a massive object, it actually distorts space-time around it. Okay, and if you have another object that you place around in that distorted space-time, while it tries to go straight, it's going to end up going in an orbit. So now if I have two objects, they are going around in each other's distorted space-time. So think of this as if you had a boat on the surface of water. So on a calm lake, when you put a boat on it, you have disturbed the surface of the water. Now when the boat moves, यहाँ का पानी has to come back up, the water here has to go down. So you are creating a disturbance because of that movement. Same thing is happening here. You have space-time which has been distorted by a star. When that star moves, that distortion was first here, star moved this side. So now the distortion has to be here. So that spreading, that change is going to create waves in space-time. Okay. If you don't follow this, that's okay. I don't follow it either, because intuitively space-time is a very weird concept. Okay, you don't have to follow it intuitively, that's okay, as long as you can work through the math and agree with it. Okay, and those who want to do the math right now, raise your hands. Thank goodness, डर गया था मैं. I pretend to not see these people here. Okay, so okay, so what happens is that as these objects are moving around each other, that is generating gravitational waves. And we detect them using these extremely massive, gigantic gravitational wave detectors. So this is one of the LIGO detectors in the US. You see that this is a central lab and there are two arms in a L shape. Those arms are 4 kilometers long and in them is vacuum, and you have a laser bouncing off from here to there and back, another laser bouncing from here to this end and back. And based on this, we can actually measure the relative lengths of those arms extremely well. That is measuring space. So if a gravitational wave goes through this, it is distorting space-time, so we can measure that distortion and we can detect gravitational waves. We have detected them for a large number of objects by now. This is an older animation, but these are all animations of various black holes slowed down, so you can see time up here, and these are animations of black holes. This was the first ever event detected on 14th of September 2015, so 150914. Two black holes orbiting each other. As they orbit, because they are creating these waves, they are losing energy, so the orbit shrinks and these then finally collided with each other. Now black holes don't emit light, but you can have artistic impressions of what you would see if you were close to these black holes. In practice, you would be going more like, I'm being torn apart, but let us assume that you pull a little bit of Interstellar, where black holes are large enough to cause gigantic tides but somehow don't destroy your ship, because Hollywood. And then what you would see is that as this is extremely slowed down, so these black holes are actually doing lensing, distorting the light as it comes across. And you saw, let me play this animation again. So you can see that as they are orbiting, you would see all of these images of the background dancing around. That is because light from the background, as it is passing close to that black hole, is being bent by the gravity of the black hole. This is called gravitational lensing, and it creates all kind of awesome effects. So you can see that there are images going in different directions and so on. There is also an app for that, by the way. So there is an app called Stretch and Squash from Laser Labs. You can put it on your phone and it will show you what would happen. You point it at anything and it will show you what will happen if a gravitational wave passes through that. There are existing 3 gravitational wave detectors that have operated so far, 2 in US, 1 in Italy called Virgo. There is a 4th one coming online called Kagra in Japan, and the 5th one is going to be LIGO India. This is going to be located in Maharashtra at a site called Aundha Nagnath. So LIGO India will join this group soon. Okay, so we are talking about LIGO and we are talking about gravitational waves. If we have 4 detectors already, why do we want another one? So here's an illustration. Okay, I showed you an animation of this event called GW 150914, which was the first gravitational wave event ever detected. Now the way LIGO figures out where a source is on the sky is very similar to how your brain processes information to figure out where a sound is coming from. Okay, so if you hear an airplane, then you can only roughly say, okay, maybe it's somewhere there. Okay, and now depending on the wavelength of the sound, your brain actually does very fancy data processing. For certain wavelengths, it actually looks at the phase difference between the signal received between your left ear and right ear. At other wavelengths, it looks at the time delay between the signal between the two ears, and based on that you can find out where the source is. Okay, LIGO does something very similar. We look at signals detected by the different detectors, and based on that we figure out where the source was on the sky. So this was the region of the sky, this grey banana that you see here was the region of the sky where LIGO said that black hole source was located. If LIGO India had been operational at that time, or if we have another similar event with LIGO India operational, we would have localized it to this region, which is about 100 times smaller. Okay, so we get much better information. There are a lot of other advantages that we get by having a detector in India. So LIGO India, excited, stay tuned. If you want to have more information about it, these are the sites. Now take those photos that you wanted to take. You can follow LIGO India on social media and you can get updates there. So gravitational waves ho gaya, but you were here for an astronomy talk. I have showed you only one astronomy video so far. So let's switch to conventional telescopes. Okay, so if I have an optical telescope, radio telescope, X-ray telescope, and if I see this, so by now LIGO has detected close to LIGO, Virgo, Kagra, the collaboration, gravitational wave detectors have detected close to 100 black hole mergers. Okay, and if we point a conventional telescope to that, here is what we see. They are black holes, they don't emit light. We see nothing. But we should go back to this event that we saw, okay, which is two neutron stars merging with each other. Now let's look at this again. The blue things that you see going out are just depictions of gravitational waves. Gravitational waves don't look blue. But as the neutron stars collide, they are actually launching these massive jets on two sides. There is a bunch of dust that is, or ejecta as we call it, that has been thrown out. And that ejecta is where we had a lot of neutrons moving at relativistic speeds. So there is a special process that goes on there called R process nucleosynthesis, which is where all of these heavier elements in the periodic table actually get synthesized. Okay? And now because neutron stars actually are not black holes yet, they have a surface, they can emit light. So this merger actually emits a lot of light. And that is something which we can study with conventional telescopes. So this particular event, this is a plot of the gravitational wave signal itself. So on this axis is frequency, on this axis is time, and you can see a signal going up like this. This is called a chirp because if you convert it into an audible frequency representation, sound, then it would sound like whoop. Okay? And this is when the merger happened, and just about 1.5 seconds after that, two space telescopes, one called Fermi and one called Integral, detected this signal. So they detected a blip that was coming from the same part in the sky, and that meant that we had actually seen the explosion with space telescopes. And after that, what followed was a completely insane observing frenzy. So this is an animation made by one of my students, undergrad, just like most of you here are. And each blob that is coming up is when a telescope actually took data on that object. Okay, and you can see there is one telescope in Antarctica. The green squares are radio telescope, red circles are optical telescopes, and observations continued for a long time. Northern hemisphere telescopes could not do much because the object was located south, and it was 170817, so it occurred on the 17th of August 2017. 10 days later, observations still went on. I can keep playing this for a very long time, because even 5 years after the merger, we are still studying that source with a variety of telescopes. But right now what I want to point out is that 3,500 astronomers from 1,000 institutes around the world actually participated in this study. In the gravitational wave side of things, in the optical and X-ray and gamma ray and radio observational side of things. And the paper that was published had an author list and affiliation. Okay, this is the largest astronomy collaboration that I have seen for follow-up of any event. You are used to seeing all these extremely pretty pictures of astronomical objects taken by telescopes. When we are working with data, we are interested in the data part of it, not in how pretty it looks. See, so you don't. Okay, the mic is out of battery. Thank you for catching that. Am I audible? Sorry, should I hold it?
No.
Oh, okay, I'll keep it. Okay, am I audible again? Was it better when I was not audible? Okay. Okay, don't touch. Okay, got it. Okay, so you can see that there is a point source here, and it's better seen in some images than others. This source was not there when the galaxy had been imaged just a few days ago. So this was a new source that popped up, and this is what was the merger site, and this was the explosion, light from the explosion that we are seeing. And look at this. Can you see that dot here? Not quite, right? But a lot of wide field telescope images actually look like that, and we do image processing and we actually can quite clearly detect this source there. So I could have put more pretty Hubble images or something of this source, but I purposely put this in here because I wanted to highlight this, that data, the way we look at it, we have different goals, and whether it is aesthetically pleasing or not is often at the bottom of our list. All right, so why am I talking about this merger? Well, what is plotted on the screen right now is this R process nucleosynthesis stuff that I had talked about a little bit earlier. So what is plotted on the x-axis is the atomic mass number, and y-axis is the relative abundance of these elements. And you can see that there are lanthanides are all present here, and this plot is a theoretical prediction of what kind of elements and how much of them would actually be created in merging neutron stars. Okay? And looking at our data, which again does not look extremely pretty, but by looking at, whoa, this jumped ahead by like 100 slides. Okay, I think I am just going to stand here. I have no idea how it managed to jump 20 slides at a time. Okay, so looking at this data, you see all of these little bumps and wiggles over here. Okay, each of these actually is a signature. You see these small undulations, they are all signatures of different elements in the spectrum, and by analyzing these, we actually concluded that all of these elements actually had been formed in the neutron star merger. Okay, and that merger is what spread them around. We call this enrichment, and with that enrichment, so all of this, by the way, must have happened somewhere in our cosmic neighborhood 10 billion years ago or 5 billion years ago maybe, because from the ashes of this merger, the sun was formed and the solar system with it, and Earth among that, and that is how there already is gold on Earth. Okay. Here's some context. Okay, how much gold? Well, let's start with mass of the Earth. It is 6 into 10 raised to 21 tons roughly, and about 0.000, so about 10 raised to minus 17 of that is gold. Okay. Curious number, by the way, Indian families own about 10% of all the gold on Earth. Now this is, you can check this, and if you find that it is wrong, please let me know, because I find this hard to believe, but apparently we do. Families may wo include kar diya probably. Okay, but now, so this is just for reference. Okay, how much gold is there on Earth? Now in this neutron star merger, how much gold do you think will have been produced? Okay, so let's guess. Okay, so this is the amount of gold as compared to Earth's mass. Okay, so I'll give you 3 options. Option 1 is about this much gold. Option 2 is 1 earth mass of gold. Option 3 is even more. So how many say about this much gold? How many say about 1 earth mass of gold? How many say even more? Wow, lot of greedy people here. Okay, so yes, this is how much earth masses of gold was produced. So calculations indicate that somewhere between 100 to 200 times the mass of the earth, not the mass of the gold on earth, 100 to 200 times the mass of earth itself is how much gold was actually produced. Okay. Naturally, of course, we are a full Indian crowd sitting here, so we will wonder how do we get more. Okay, so well, Indian astronomers have been active, not just for literal gold, but also this is a gold mine in terms of the physics that we can learn from this. And we have a lot of telescopes in the country, okay, and a lot of these were active in these follow-ups. So this is again the size, the red symbols again show optical telescopes, green are radio telescopes. Astrosat is not located in Afghanistan, it's in space. I didn't know how to show space on a 2D map. But a lot of telescopes and all of these were actually involved in following up. In particular, there is one collaboration that I would like to highlight here, which is something like this where science is so crucial, you can't rely on one small team doing something, right? We had 3,500 people working together, and that is a superset of a lot that is seen in this field, which is people getting together and collaborating to understand the biggest and most interesting questions in the universe itself. So what we have here is a collaboration called GROWTH, Global Relay of Observatories Watching Transients Happen. Next time you watch Marvel movies and think of SHIELD and Hydra, we have a more complicated acronym than that. This is a network of telescopes around the world, and the idea is as follows. Imagine that there is an object over here, which is, say, we start off with the Zwicky Transient Facility in California, which discovered a transient, some new source. What's going to happen is as the earth rotates, that source is going to set, but it will rise in Hawaii. So we hand it over to our partners in Hawaii, from there to Japan, Taiwan, India, Israel, Canary Islands, and then back to US. And through this network, we can actually continuously observe any source that we want to study. As a part of this, we have set up the GROWTH India Robotic Telescope in IO. That's the dome, the video that you saw to begin with. Those who came late, oops. All right, so GROWTH India Telescope is a 70 centimeter telescope. So that's, the mirror is about this big in size. The mirror is located here, and we have this camera here. Note that I am showing off by saying this is a 4K by 4K high QE CCD. That translates into 16 megapixels. How many of you have phones with more than 10 megapixel cameras? Quite a few, right? So why am I showing off about a 16 megapixel camera? The efficiency, the QE, quantum efficiency or the sensitivity of this camera is far, far higher than the sensitivity of your phone cameras. How much higher? Let me translate that into a rupee amount instead of phone cost, instead of some technical details. So how much do you think the camera of a phone costs? Few thousand rupees? If you have a high-end phone, maybe 10-20,000 rupees. Okay. This camera costs about 1.5 crore rupees. Okay, and that is because it is that much more sensitive. Here's the site, Hanle. If you are any time planning to visit Ladakh and you want to visit Hanle, you drop us a China border. There is a lot of background that we have to take care of. So what we want to do is we'll make sure that you can get clearances and you can actually go and visit the telescope. You can visit it in daytime, by the way, not at night. Why? रात को काम कर रहा है यार, disturb मत करो. Okay, you will drive them there on your motorcycle, because that apparently anyone wanting to go to Ladakh has to either buy a 4-wheel drive or a motorcycle, and then you'll shine your headlights. We are trying to observe lights which are about 1 billion times fainter than that. You will ruin our entire observing. Okay, so night sky is extremely dark. Here's still from like the movie that you saw earlier. Here's the telescope nicely sitting inside the dome. So this is, you'll notice by the way that there is a very uncomfortable small chair over here and not much place to sit. And the reason for that is we don't want anyone sitting there. Okay. So I study transients, I study these explosions, right? So first time you get a call at 2 a.m. saying that, okay, let's make it 4 a.m. Most of you probably don't sleep by 2. So when you get first time you get a call at 4 a.m. saying, hey, there's a supernova that's exploded in a nearby galaxy, let's observe it. You get extremely excited. You say, yeah, let me go. And you either, if you are the observer, you run to the telescope, or you call up your observer friends and you tell them to go to the telescope. Then you point the telescope, you get data, very exciting. By the time you are doing it for the 5th time, you are like, oh, theek hai, haan, aata hu. And by the time you are doing it for the 500th time, you are like, sone de yaar, roz udta hai ek supernova, kaun uthega? But the universe doesn't wait for us, right? Universe doesn't say that let me conveniently blow up supernovae only at 8 p.m. Of course, you can't, if they blow up in daytime, you can't do anything. So what do? What you do is that you actually automate the telescope. So this is the only robotic telescope in the country. And undergraduate students from IIT Bombay have done most of the automation work by the way. So what happens is if there's a transient, the telescope can automatically respond to notices that are broadcast by other astronomers. It will end the current observation, repoint to that new direction, start taking images. Then it will send me a message on Slack saying, hey, I've started observing. And if the event is even more important, the telescope first starts observing and then calls us up on our phone saying, we have started observations, please log in to monitor them. Okay, that means that astronomers don't need to stay up all night. They can actually be fresh and working in daytime. And that's where the scientist is really needed to do the creative part of science, to actually connect the dots, to actually understand what is going on. You don't need to be a very highly trained astronomer to just point a telescope to some place. So you let the robot handle that. So this is for ground. What about in space? Well, we have this extremely sensitive space telescope called AstroSat, which Rajesh mentioned in the introduction. I was lucky to be part of the team that built one of these instruments called the cadmium zinc telluride imager. Now AstroSat does a lot of things, but in particular, one of the things that it does is it can detect explosions in space. Okay, we call these as gamma ray bursts. The kind of signal that we saw with Fermi and integral early on. So here's an example of a GRB detected by AstroSat. So what is plotted on this axis is time in seconds. And there are 4 quadrants on AstroSat, CZTS, so 4 independent detectors that are identical to each other. And you can see here that they are measuring some background counts fluctuating up and down as a function of time. But as I play time forward, then suddenly we see this extremely sharp and strong spike. So this is a GRB. Okay. So, and AstroSat in the last 7 years had detected well over 500 of these GRBs. In terms of the global record, we are in current active satellites, we are either 3rd or 4th. That we are in a close race with an instrument called integral. So that means we should have seen 170817, right? See, that's what happens when the presentation advances too early. You already saw the joke without knowing what it was about. But we did not. Okay. And we calculated the intensity and we should have seen an extremely clear detection by AstroSat, but we did not. So you have an awesome telescope which is supposed to detect this and it does not. What does it mean? Kuch to gadbad hai. So in this case, the gadbad was that the event was hidden behind Earth. Okay, so this is the part of the sky where Fermi thought that the event is located, and eventually it was found here, where my pointer is sitting right now. And then this white circle is the part of the sky that was not visible from AstroSat at that time. Why? AstroSat orbits around the Earth. It is in what we call a low Earth orbit, 650 kilometers above the surface of the Earth. So the Earth blocks 1/3 of the sky. And no matter how sensitive your telescope is, you cannot quite see through all of Earth. So as a result, AstroSat missed this. And I kept talking about this event in 2017. What happened later? Well, a lot happened later. LIGO detected a lot more gravitational waves. They detected a lot more black hole sources, neutron stars, binary neutron stars, black holes, all sorts of combinations. But despite all of these detections, no electromagnetic radiation was seen from any of them. Okay, and this is unfortunate because we learnt a lot from the first. 4 years after the event was observed, people were still publishing on an average 1 paper on that event per day. Okay, and as of today, that has slowed down to 1 paper every second day. So there are 1,500 papers published on this object, because it's literally a gold mine created 100 times Earth's mass in gold, and also a figurative gold mine, because it taught us a lot about physics and astrophysics of such kind of sources and such kind of events. So why did we not see it? Well, these events were further away, so they would just be fainter, and current satellites are not good enough to detect those. So how do we handle this? Well, if you are going forward and you want to do something better, you need something that is maybe an order of magnitude more sensitive. You should never blink. You don't want a scenario where you have a sensitive telescope on the wrong side of Earth, and you just don't want to see the event, you want to study it, you want to understand it, which means that you have to get a broadband spectrum which will allow us to infer a lot about the physics of the source. And in order to do that, now we are talking about something that is going to work 5 or 10 times better than the current world best satellites, which are Fermi and Swift, which are NASA and ESA missions. And you need to be very ambitious to aim for something bigger, and that's exactly what we have done. So we have this extremely ambitious proposal called Daksha, which is a completely Indian proposal to build not just 1 but 2 satellites that will be far more sensitive than anything that has ever been built before. These satellites will be sitting on opposite sides of Earth and continuously monitoring the sky. The area is 6 times larger. So just some comparison. Okay, if you are not technically minded, you can ignore this. But the effective area, how large our detector is, it's about 6 times bigger than Fermi's detectors. We can cover 100% of the sky with 2 satellites. For comparison, Swift-BAT covers about 11%. It is a broader energy range than any other satellite, which is extremely important to detect thermal components in spectra. What can we do with all of this technology in our hands? Well, we can detect dozens of binary neutron star mergers per year. Remember that so far the score is that the entire world working together, since the dawn of gravitational wave astrophysics, which is 2015, in 7 years we have seen 1 source. We are now talking about detecting dozens of sources every year. We will also detect about 500 to 1,000 GRBs per year. We can localize them and all sorts of things. But there's also something interesting, which is that Daksha will allow us to look under the rug. Okay, so how does LIGO say that we have detected a source? It looks for a signal. So the gravitational wave detectors, LIGO, Virgo, Kagra, look for a signal. The signal needs to be of a certain strength to be sure that it was not a spurious result. We call this signal to noise ratio. And if you imagine that they have set some threshold saying that, okay, you have to have a SNR of at least 8 for the event to be detected, to be confident about the detection. What happens if you have an event which is 7.9? You are going to reject it. With Daksha, what we can do is we can actually tell LIGO, hey, there was an event at this time in this part of the sky. So you can actually do a restricted search, and our calculations suggest that we can actually boost the number of events detected by LIGO by a factor of 1.5 to 2. So just because we told them where to look, okay, imagine that you are in a jungle and you are trying to hear bird calls, for example. Okay, if I just ask you what birds did you hear, you might miss something. But if I ask you specifically, did you hear a parrot among them? Then you can listen to the same audio again and you will be more careful and you can identify that even if you missed it the first time. So that's what we can do here. So that opens up a huge discovery space. Okay. Again, a comparison. This is, we considered a lot of different models about these binary neutron star mergers. And each of these axes here is one such model. And what is plotted along each axis is how many events per year can be detected by different missions. And you can see that every time the blue curve is the largest, that's Daksha. And inside that, these tiny little ones are Fermi and Swift, which are the current world leading telescopes for this. Since I'm talking about Daksha, I'm going to take a small detour here and talk about what else Daksha can do, because it's not just about LIGO counterparts. We talked about it here in that context, but there's a lot more science that this very, very ambitious mission, you can't have it doing just one thing, right? So there's key science, what we call EMGW is what we talked about, which is electromagnetic counterparts to gravitational wave sources. We have the the best sensitivity in those terms, but we will also study a lot of gamma ray bursts. We will detect gamma ray burst at the highest redshifts when the universe was extremely young. The only mission that can do prompt soft X-ray spectroscopy of GRBs. We can actually do very finely time-resolved studies which can't be done with current missions. So we'll be tagging photons with microsecond accuracy. Every individual photon hitting the detector, we'll count it as a separate one. We can also do polarization measurements, and the polarization sensitivity is on par with it is better than any existing mission, and on par with highly niche missions which can do only polarimetry. So few collaborations have proposed such missions saying we want to study polarization of GRBs. That's all that mission can do. And our sensitivity is the same as them. But then there is a lot of secondary science that we can do. Okay, and that's a huge list. We can monitor pulsars. So neutron stars as they spin can actually pulsate. In the radio that is seen very commonly. It also happens in X-rays. So we can monitor X-ray pulsars. And as you can guess, next thing I'm going to say is highest sensitivity in the world for that. We can monitor magnetars, soft gamma repeaters. TGFs is something quite cool. It's terrestrial gamma ray flashes. It is gamma ray emission that is associated with lightning on Earth. And so if you are a satellite in low Earth orbit, you can actually detect those, and that helps us understand thunderstorms and lightning and other things better. We can also study the sun, solar flare measurements. We can study sources as they get hidden behind Earth, and we can monitor a lot of the sky by that. This is something which is quite cool. How many of you have heard of something called dark matter? Okay, so most of the matter in the universe is dark. We don't see it. We know it is there because we feel its gravity. One potential way of having this dark matter is something called primordial black holes. So remember the periodic table we drew? At the Big Bang we had hydrogen, helium and a bit of lithium. What if the Big Bang also created a lot of lightweight black holes, say 10 raised to minus 11 to minus 14 times the mass of the Earth? They are too small, so they won't actually be accreting matter. They won't be visible in the normal way that we detect black holes. But what we can do with Daksha is that by studying how they affect other sources that are being studied, we can actually detect those. So when you have a highly sensitive instrument, you can actually gain a lot of information from it. Okay, and we are actually building this. So Daksha has been shortlisted by ISRO as a mission for study, and they gave us seed funding. So we have developed a prototype, and we are now going to go through a series of reviews. The first of which is actually on Monday, after which ISRO will decide whether this mission should be launched or not. Okay, so that brings us quite close to the end of our time. So I will wrap up here, and I'll leave you with this. If you want to know more about Daksha, you can go scan that QR code and you can go to the site to get more details. And I guess we can break here for questions.
Thanks for the talk. So you mentioned SKEV to MEV. So and what I missed the part that what do you observe in the end? I mean, is it? I mean, like photon, like for example, Fermis and other satellites are observing, like several type of particles, correct?
No, all of these satellites are observing photons. So KEV to MEV is actually also, so we have these three types of detectors that will cover, so these are low energy detectors that will cover say about 1 to 25 keV, all in photons. So this is soft energy, this is medium energy X-rays 20 to 200 keV, and then at high energies we have scintillators which will cover from 100 to above an MeV. Interesting thing is that all of these detectors actually have Indian space legacy. So these have been flown on Indian missions before.
Okay, thanks.
In the last point you mentioned about the black holes, right, which are very small compared to Earth's mass. are there any proofs for that? Like, do they exist? Like,
We have not found any yet. And the problem is this: how do you detect a black hole? Right? Black hole looks like this. Okay, so the way you see a black hole is that you detect it by its effect on its surroundings. So either there's a nearby star which is being stripped apart, or in centers of galaxies we have these supermassive black holes, everything is orbiting them. Famous case is center of our own galaxy, where we have seen stars orbiting it, or you might have seen the Event Horizon Telescope image and so on. These black holes are so small that they will not have any direct observable effects. So the way we will see it is through gravitational lensing. So if I have a tiny black hole sitting here, and as suppose there's an event in the background which happens, as that light is going past that black hole, it will get slightly lensed. And because we have two satellites, we can actually measure the difference in the signal seen by those two, and that will allow us to detect it. So actually no other instrument to date is capable of probing that black hole range, which is why this is important.
okay.
There's- yeah.
But if it's such a small black hole, then wouldn't the Hawking radiation would have killed it already?
Correct. So the question, since you're not on the mic, the question is there is something called Hawking radiation which can actually cause black holes to evaporate. And wouldn't Hawking radiation have killed these off? Well, they are 10 raised to minus 11 times Earth's mass. So in terms of actual mass, or say 10 raised to minus 14, 11 to 14 is the range we can probe. So we are still talking about something that is 10 raised to 20 kilos. That will take a lot longer than the lifetime of the universe to boil it off with Hawking radiation. Yeah, I think, so he's choosing the questions. It's great to see there are a lot of questions. We can take only a few of them.
Sir,
Yes.
what is the advantage of, seeing such small black holes?
Oh, that is very interesting. Why do we care is essentially the question. Because we have no idea what dark matter is. Don't you want to know what 70% of the universe is made of? Not even 70 actually. So normal matter, does anyone know how much of the universe's mass energy budget is made up by normal matter? Right? Only a few percent, right? And then we have about 6 times as much dark matter, and about 70% of the universe is something called dark energy. We have absolutely no idea what these things are. Right? And then all of astrophysics is about trying to find out what exactly is going on out there. So we want to know if so for example, if these kind of primordial black holes make up dark matter, then life is easy, because then it means that our so-called standard model of particle physics is complete. It means that the periodic table is complete. But if they are not, then we need to figure out something else, something which we have completely not understood yet.
Sir, how is dark matter related to the concept of finding these primordial black holes?
So let me try to rephrase that. So we don't know what dark matter is. Okay. There are multiple models of what can be out there, which is not like normal matter, but has as much mass. So one idea is exotic particles. We have tried a lot to find them on Earth. We have not. In experiments, in natural experiments, in particle accelerators, we have no idea. So then you say, okay, can I take something that we already know and somehow distribute it in such a way in the universe that we would still not see it? And that is where primordial black holes come in. That you could make these tiny, such a low mass black hole can't be made from astrophysical processes. When a star dies, the smallest black holes that we know or we know of that can be made by that are at least 5 times more massive than the sun. Okay, so now you want to make something that is much lighter than the sun, because we probed, we said, okay, can we have 5 solar mass black holes making up dark matter? The answer is no. We have probed a lot of different mass ranges. If they are ultra light, then Hawking radiation would have destroyed them. But there are these mass ranges in between where there is still a possibility that those could actually just explain all of dark matter. Do we have any reason to believe that they will? Not any more than any other particle or any other explanation of dark matter. We are grouping in the dark for dark matter. Yes.
Sir, will this satellite be able to detect vampire stars?
Vampire stars. Okay, so what do you mean by vampire stars?
Actually, it's basically
a two-star system where one star it eats away the
Yes,
mass
okay.
of the other.
So there is something called interacting binaries, and in particular neutron star and black hole X-ray binaries are scenarios where matter from one star is actually being sucked up by the compact object companion, and yes, we will actually see a lot of them. We will study them as X-ray pulsars, because if there's a neutron star is your vampire star, then you get X-ray pulsations. We will also study them when they go in outbursts. So yes, we will actually be able to detect those.
Okay, let's thank Varun for a wonderful talk. We will break for the tea. You can bother him there. I hope he doesn't mind.
Of course not. Thank you.